So as I've said, we've looked at these Riemann sums, which give us an approximate area, right? It's a better and better approximation of this area as we get closer and closer. Um, but in practice, actually calculating the area with the Riemann sum is just, downright tedious. Most of the time it's impractical. If you're trying to code it into something, it's even worse. It's super inefficient computationally. And there's this really nice theorem um, called the fundamental theorem of calculus that was discovered independently by two different mathematicians of calculus. Sir Isaac Newton and Gottfried Leibniz are the two mathematicians who separately invented calculus in the early 1700s, I believe. And there's this very nice theorem, and it says this. Right? It says, let f be continuous on some interval ab, then the definite integral from a to b of f of x dx, it's capital F of b minus capital F of a, where f is any antiderivative of f. So that is f prime, capital F prime as lowercase f. So what this is telling us is that definite integrals also have something to do with anti-differentiation. And you may have absolutely guessed that based on the fact that, well, they use the same symbol. But it's not necessarily intuitively obvious, right? I'm going to jump into some examples here, and then at the end of the lecture, we'll go through a sort of a sketch of an idea of why this might be true. Not a full proof. It takes a lot of machinery for that, but sort of giving us an idea of why this might be the case, because it's definitely not obvious that these areas and these derivatives have anything to do with each other whatsoever, which is why this is such an important and fundamental theorem. There's a piece of notation here. It's often really nice to write if you're doing f of x. So we saw this, right, which means plug in at a. But a thing that we'll use a lot is this vertical bar with a b in the superscript and an a in the subscript to mean f of b minus f of a, right? And with this notation, the fundamental theorem becomes the integral from a to b of lowercase f of x dx is capital F of x evaluated between a and b, right? This is just a sort of different notation for this. And we'll work ourselves through a whole bunch of examples. So we want to consider, there's a horrible vertical line. The dots only do so much. So we want to consider one of our very basic functions, right? We'll call this guy 1, and we'll call this guy 3. And say we're looking for this area here, right? This region R. and we want to find the area. What this is equivalent to saying is looking for the integral from 1 to 3, because those are our bounds. This function here, this is just y equals x, so it's x dx, right? And you could do this sort of geometrically and divide this into what is a rectangle and what is a triangle. And we can sort of check our answer that way, but why don't we try to work it out this way, right? What's our antiderivative going to look like? Well, the antiderivative of x is going to be 1/2 x squared plus c, and this needs to be evaluated from 1 to 3, right? So everywhere we see an x, first we plug in a 3, so it's going to be 1/2 3 squared plus c minus, and it's important to remember that we're subtracting this whole expression, 1/2 times 1 squared plus c. So this looks like it's going to be 9/2 plus c minus 1/2 minus c, which is 8/2 or 4, right? And that makes sense, right? This is going to be, this part right here, this is going to have an area of 2 times 1, or 2, right? And this guy's also going to have an area of 2, right? 1/2 base times height, and that one is just base times height. And so we get 4 units, okay? But one thing to notice here is that when we choose our antiderivative 1/2 x squared plus c, we're adding c in the first instance, and then we're subtracting c in the second instance, right? Capital F of b includes the value c. Capital F of a also includes an instance of c, but we're subtracting the two. So they're going to perfectly cancel out, right? Which means when we're doing these computations of a definite integral, not of an indefinite integral, but of a definite integral, we can just drop that constant of integration because we don't need to worry about it, right? It's going to get added and then subtracted, and it's a 0, so it doesn't affect us, right? So let's look at a function that has a little bit more to it, right? Let's go back to x squared. Right? Our parabola, that's going to look like that. What's this area here? If this is 1, right? What is the definite integral from 0 to 1 of x squared dx? Well, we need to take an antiderivative, right? That's what the fundamental theorem of calculus allows us to do. So it's going to be 1/3 x cubed, which is our antiderivative of x squared, evaluated from 0 to 1. But what's really nice is when you evaluate this guy at 0, it just goes away, right? So it's going to be 1/3 times 1 cubed minus 1/3 times 0 cubed, or 1/3, which is precisely what we guessed using our Riemann sums, right? Using those Riemann sums, we got 1/3. Now that we developed this, much higher level tool of this fundamental theorem of calculus that Newton and Leibniz have now sort of handed from on high, but it agrees on this case, which is a good sign, right? If it didn't, we should be, rather worried, right? What about something like this? What if we take that x squared and we shift it up a single unit and look at x squared plus 1 from, say, I don't know, -1 to 2, right? What is this area? Well, once again, we can use this fundamental theorem of calculus, right, to say that the definite integral from -1 to 2 of x squared plus 1 dx, remember this is exactly what our area is. Well, I want to take antiderivatives. What's the antiderivative of x squared? Well, it's 1/3 x cubed. The antiderivative of 1 is x, and remember we don't need to worry about a plus c. And then we need to evaluate this between -1 and 2, which means we take 1/3 times 2 cubed plus 2, and then we subtract 1/3 times -1 cubed minus 1. This looks like it's going to come out to 8/3 plus 2. That looks like plus 1/3, right? Because we're minus a negative, and then minus a negative again. So plus 1. So we have 9/3 plus 3. So this is going to come out to 6, right? There's exactly 6 units of area under this curve between those bounds, right? And of course, we can separate this from the idea of, areas, and we can just evaluate these definite integrals without having to think about what the graph looks like, right? What if we tried something like the integral between 1 and 3 of 3x squared plus e to the x dx. As we take our antiderivatives, right, what are we going to get? Well, looks like we're going to see the antiderivative of 3x squared. Well, that's x cubed, right? The antiderivative of e to the x is e to the x, and again, we don't need our plus c. I'm going to evaluate this between 1 and 3. 3 cubed is going to be 27 plus e cubed. And then we need to subtract 1 cubed plus e to the 1. And unfortunately, not a lot of this is going to simplify, and we're just going to get 26 plus e cubed minus e. This is as simplified as it gets. I mean, I suppose if you really wanted to, you could factor out a common factor of e there, but this is completely fine. Of course, we can also say chew on something like this. What about from 1 to 2 of 1 over x minus 1 over x squared? Now here, we already have to be a little bit careful. Remember, we can't deal with discontinuities yet. We'll talk about that again, maybe depending on time. We'll spend a little bit of time considering. Using the tools we develop next week, we'll be able to integrate over very, very nice piecewise functions, right? Something that's, a function and then something else. There's no like big zooming off to infinities. Both of these have vertical asymptotes, but the vertical asymptotes are at x equals 0, right? And since the vertical asymptotes are at x equals 0, and we're outside of that range, we're all good. If this was a negative, can't really do anything, right? With that negative, all of a sudden we're trying to find the area under a graph that zooms off to infinity. Like that doesn't make any sense, and so we just simply can't handle that. But we're not dealing with that case. We can deal with this one. It's going to be a little bit easier to write this from 1 to 2 as 1 over x minus x squared. or sorry, minus x to the negative 2, because then we can use the power rule a little bit easier, right? Because when we take antiderivatives, we're going to get the natural log of the absolute value of x. That's my antiderivative of 1 over x. And then this is going to be plus x to the negative 1. How do I know that? Well, this negative 2 is going to drop down and we add 1. All right, so it's going to be 1 over negative 1, which is negative 1, which is then going to cancel with this negative, giving us a positive. Then we add 1 in our exponent, and we get negative 1. Okay. So now that we have this, once again, we need to evaluate this between 1 and 2. So this is going to give us the natural log of 2, because 2 is positive, plus 1/2 minus the natural log of 1 plus 1. But notice, right, the natural log of 1 is equal to 0, right? Anything to the 0 equals 1, so the natural log of 1 is 0. So then our function, or our answer, right, is going to simplify to the natural log of 2 minus 1/2, right? And this is where I do want to pause it and remind you of something that we said last lecture. These antiderivatives and these definite integrals, right? There's a reason that on Tuesday I try to say antiderivative more often than I say indefinite integral, because they are very different and it's so easy to get them confused, right? But an antiderivative is an infinite number of functions. It needs a plus c. A definite integral is a number. It's some finite value. They're intimately related, right, via this fundamental theorem of calculus, but they are distinct, right? They are different things. And you know, I think that the notation here is really good, but it does lend itself to a little bit of confusion, right? When the only difference between the symbols is whether or not you have those bounds there. Sort of shifting gears a little bit, let's talk about net change, right? What is often a little bit more maybe not useful, but a thing that we're more interested in sometimes in the real world is the net change of a quantity over time, right? Say population, right? The net change in population, right, from time A to time B is this: the population at time B minus the population at time A, right? Subtract the two, it's the net change or the total change. But notice, if we have a continuous derivative, right, then we can write this like this: the integral from a to b of p prime of x, or we can call this t actually, because we're doing it with respect to time, p prime of t dt, right? Again, this is as long as p has continuous derivative. If it doesn't, well, then the tools we've built in this class kind of fall apart. And, you know, the first time I saw this, it didn't really make very much sense to me. But here's what I want you here's how I want you to think about this, right? P prime is our derivative. It's some little tiny change, right? And my integral, my definite integral, comes with the idea of adding up all of these little slices, right? All of these little slices of these rectangles, we're summing all of those up, right? Some people think that that's why this is vaguely shaped like an X, right? Because it's a sum. And if I sum all of the little changes in a region, right, all of the little tiny steps, well, shouldn't I get the total change, right? When I don't know if that was like a thing that was intuitively obvious to you, but the first time I saw this made no sense to me. But then someone explained it like that. Well, if you add up all of the little changes, of course you're going to get the total change, right? The whole is the sum of its parts in this case. The whole change is the sum of the little changes. But anyway, let's say we have some population. Say we know this population changes at the following rate, right? So say rate of population growth is R of t is 13,680 t squared minus 170 788 t plus 23. Sorry, 234 633. Right, some monstrous function that you just happen to know, right, for whatever reason. And this is for t between 0 and 3. This is how fast we're growing. Well, we can ask total population size, size change, I guess we'll say net change, from, say, the second decade, or from t equals 1 to t equals 2, right? If each of these are decades, I guess you'd have the 0th decade, the first decade, and the second decade. And so we're looking for p of 2 minus p of 1, right? The total change of our population. But of course, as we just saw, we can find this by taking our antiderivative of p prime of t. But p prime of t is going to be my population change, right? How fast my population is changing. And so this is going to be r of t dt. And from here we can carry this through, right, just how we have our previous ones. Right, this is going to be the definite integral from 1 to 2 of, and I'm actually going to copy this function so I don't have to write it again. Right, all of that guy dt, right? And here we just take antiderivatives, right? And working with these coefficients is a bit nasty, so I've gone ahead and cooking showed the math a little bit. 44,560 t cubed. When I divide that second coefficient by 2, it's going to come out to 89,394 and 243,633 t's. That should be a t squared. And then we evaluate this between 1 and 2. Right? And at this point, this is a calculator exercise. Obviously, as I've said a number of times, we don't need calculators in this class. This is more an example to show you how it could be used. I wouldn't ask a question with numbers like this on an exam. But when you run that through your calculator, you're going to get 278,371, right? So this is going to tell us, right, how much the population changed total. And notice this function, you have p of 2 is greater than p of 1. There's nothing necessarily stopping us from doing that, right? Our function could totally be such that the net change is negative. There's instances where we wouldn't necessarily want that if it were, say, the net change in yearly revenue, like that would be bad. But it is absolutely possible. And so, with the little bit of time that we have left, I want to sort of talk you through um, why it might be the case that this fundamental theorem of calculus makes sense, right? This is much more the sketch of an idea than it is a proof. But say we have, your favorite function. Maybe they look like that. And we're looking at the area from A to B. Okay. And here's what I want to do. I want to actually define a function, pick some intermediate value t, and define a function to be this area, right? Where t ranges between A and B. And here's what I want you to think about, right? Just with our Riemann sums, right? As our n got smaller and smaller, or as our n got bigger and bigger and bigger, and the width of our rectangles became shorter, right? We got a better and better approximation of that area. And so here's what I actually want to think about, right? Since we're trying to get this in terms of some sort of derivative, what happens when I take some tiny step here to t plus h? Obviously, I have to exaggerate the size of the step. But let's say we take some tiny step here. From here, right, what is the area of just this little rectangle, right? Well, that's going to be a of t plus h minus a of t, right? That makes sense. This area here is this whole area minus this area, right? Because a gives us the area from A to t. So a of t plus h minus a of t gives us this, right? But notice that as h gets smaller, then this is going to slowly approach this rectangle, right? A of t plus h minus a of t is approximately equal to, right, f of t times h. It's not exactly equal to that, right? F of t times h would be this rectangle here, right? But it's getting closer and closer. In particular, right? Why don't we divide this h over, right? That's going to tell us that f of t is approximately equal to a of t plus h minus a of t over h. And as this limiting process happens, as h gets closer and closer to 0, what happens? Well, if we take the limit as h approaches 0, this is a prime of t, right? This is the definition of the rate of change of my area. And, right, as h approaches 0, this is a better and better approximation. And so I guess we'll draw this under here. When I take my limit as h goes to 0, we get f of t, right? Because there's no h's on this side, so f of t just sort of pulls through. But we do now get equality equals a prime of t. And this already tells us something extraordinarily powerful. For all, like everything in this region, right? For all values of t between a and b, so I just realized there should be an end to that bound. my area function is an antiderivative of the curve it's measuring the area under, right? Which is fascinating, right? And so this is already in my mind again fascinating, but we can actually go further than that, right? We know, right? What do we know? We know that since it's an antiderivative, right? A of x, whatever my area function, needs to look like f of x plus some constant c. Can we solve for this constant? Well, sure, right? Notice that a, capital A, of lowercase a is 0, right? There's no area under this one dimension, like this line here has no area, right? So a of a equals 0, right? Which means what's c, right? A of, so we know a of a is f of a plus c, right? So c must equal minus f of a. Why? Well, because it has to come out to 0. But then, right, what's the area of the whole region? Right? That's going to be a of b, right? The area from a to b. Well, the area from a to b, as we saw right here, is f of x, or sorry, f of b plus c, or since we know our value of c, f of b minus f of a. But the area of the whole region is by definition my integral. And so we get this nice fundamental theorem of calculus popping out because we decided to look for a way to write something like a derivative. I'll just write that under its own thing. And I think that deserves a little QED at the bottom. There's this tradition in mathematics that when you prove something, you write either a little box, or in my opinion, if you think the thing that you proved is cooler than a box deserves, you write QED. It's an old Latin phrase. Anyway, I know this was a bit longer of a lecture, but now you've seen the fundamental theorem of calculus, the thing in a sense that we've sort of been building to all quarter. Next week, we're going to sort of play cleanup with the rest of these ideas, see what from taking antiderivatives we can apply to definite integrals, take a quick look at how this can apply to different sorts of business problems, and actually look at, rather than the area between a curve and the axis, the area between two curves. It will actually kind of use a similar trick to this. So that'll do it for this lecture. I'll see you guys then.